My name is Dr. Jovita Nsoh from the University of Houston. Today, I present SZTIGA, a sovereign zero-trust governance architecture that positions AI-driven identity management as the primary control plane for national critical infrastructure resilience. This work integrates JEPA-based predictive threat anticipation with federal identity access management to address the growing threat of nation-state cyber campaigns against critical infrastructure. Here is the roadmap for today's presentation. We will begin with the motivation, covering the escalating threat landscape targeting critical infrastructure. Then, we will present our three hypotheses, the SZTIGA three-pillar architecture, formal models, threat models, methodology, experimental evaluation with statistical significance testing, and we will conclude with ablation analysis, discussion, and future direction. The threat landscape demonstrates an escalating pattern of nation-state attacks on critical infrastructure, from Stuxnet in 2010 to the Vault Typhoon campaigns in 2023 and Handala Striker Wiper attacks in 2024. Each incident reveals the same fundamental architectural gap, which is existing frameworks treat identity management as a peripheral service. SZTIGA, which is this work, addresses this gap by positioning identity access management as the primary control plane. On the left side of this screen, you will see four critical limitations of existing approaches for ZTA as defined in NIST 800-207. No framework governs AI agents as identity principals. Cross-domain trust for federal critical infrastructure is ungoverned, and no formal resilience guarantees exist under ADD, which is adversarial disconnected environment. On the right side, as the SZTIGA addresses each gap. JEPA provides for predictive prediction. AI agents get full lifecycle governance. Federal identity management becomes a control plane with TPM 2.0 and OPA. And finally, Gaussian process trust scoring provides formal guarantees. We advanced three testable hypotheses. Hypothesis number one is a JEPA-based predictive modeling that achieves statistically significant improvement in anticipation lead time. Tested with McNemar chi-square, we got our results. For hypothesis number two, identity-centric containment reduces MTTIC by at least 70% compared to network isolation alone. In hypothesis number three, federated policy convergence under adversarial degraded disconnected conditions maintains FPCR above 0.95 within 120 seconds. All three hypotheses are confirmed by our evaluation. SZTIGA organized around three independent pillars. In pillar number one, as you can see, the federated identity access management control plane using TPM, hardware attestation, OPA with rigor, and X.509 certificate chains for continuous authentication and authorization. In pillar number two, what you see demonstrated is that JEPA predictive threat engine constructing latent world models with formally confined training objectives. And in pillar number three, we show the national governance resilience layer aligned with NIST CSF 2.0, AI RMF, and SP 800-207A The key insight is that IAM serves as the primary control plane for security decisions. In this figure, we show that the enhanced architecture with protocol level specification. At the top of the picture, what you see is the sovereign governance layer that provides national level policy orchestration. The middle tier contains the three pillars: the Federated Identity Access Management Control Plane with TPM and OPA, the JEPA Predictive Engine, and dominance-specific policy or domain-specific policy enforcement points. The bottom tier shows the 5 CI domains, which in our case was energy, OTCIS, V2X, which is vehicle to anything, transportation, defense, and smart cities. Note that the bidirectional flows that go between the JEPA predictive or predictions and the trust score computation. Pillar number 1 implements Federated Identity Access Management as the enforcement backbone. On the left, the identity stack, TPM 2.0, hardware attestation with IDEF IDS, and attestation keys firmware for X.509 certificate chains, rooted in sovereign national CA with short-lived certificates. OPA with rigor for policy-based access control via a centralized policy deployment point and distributed policy enforcement points. And SCIM OIDC SAML for cross-domain federation. On the right, AI agents have defined identity lifecycle provisioning with SPIFFE compatible SVIDS. Continuous attestation via model fingerprinting, behavior monitoring against JEPA predicted envelopes, and cross-domain revocation through OPAM. In pillar number 2, we operationalize the JEPA principles for cybersecurity. Here, what we show in this figure are the 5-stage pipeline: telemetry collection, behavior feature extraction, latent state encoding, world model prediction via JEPA or hierarchical JEPA, and threat anticipation with confidence bounds. The training objective uses stop gradient targets with seek-rec variance convariance or covariance regularizations to prevent operational collapse. The predictor is a lightweight transformer predicting at multiple horizons from 1 to 60 seconds. The key advantage over discriminative classifiers is that JEPA predicts future states rather than classifying current observations, enabling preemptive containment. We present 3 formal definitions. Definition 2, the adaptive trust score modeled as a Gaussian process posterior with Martin 5.2 kernel. And then we had the Thompson sampling for access decisions. This naturally handles the cold start problem for identities. In definition number 3, the reliance threshold ensuring operational capacity remains above theta through preemptive containment. Definition number 4, federated policy convergence rate, targeting 0.99 within 30 seconds under normal conditions and 0.95 within 120 seconds under ADD conditions, achieved through OPA-OPAL push through policy synchronization. The threat model assumes nation-state level capabilities mapped to MITRE ATT&CK for ICS. T1, identity spoofing. T2, lateral movement exploiting cross-domain trust mapped to TA019109. T3 are AI-enabled adaptive attacks that evolve against defenses. And in T4 are supply chain compromise attacks. And finally, in T5, these are coordinated cascading attacks designed to trigger simultaneous multi-sector failure. Each threat has a corresponding SZTIGA mitigation through the 3 pillars that we developed. We follow the Agile Infused, from a methodology standpoint, we followed the Agile Infused Design Science methodology, which I started, essentially, I'm the author of this methodology, started in 2025. It's an adaptation of classic design science methodology. What a DSRM does is it incorporates iterative adversarial refinement. In definition, therefore, Red Team exercises review cross-domain federation as the primary attack surface. In artifact construction, 3 iterations refine the architecture. The first one is basic trust scoring. Then we have protocol level specification. When pilot evaluation showed conceptual descriptions were insufficient, then the AI agent lifecycle formalization with the ADD credential revocation required pre-staging. Evaluation uses McNamara statistical testing across 5 independent runs. So pretty novel invention there from our team. Evaluation uses a digital twin co-simulation environment, coupling Omnet 6.0 with MATLAB Simulink for power system dynamics. We use 5 interconnect CI domains, model realistic identity flows, and cascading failure propagation. The JEPA engine trains on 2.4 million identity events from established benchmark augmented with MITRE attacks for ICS. We compare against 2 baselines, the traditional IDS representing SNOT Suricata class systems and a standard ZTA representing NIS 800-207A compliant implementations. All comparisons employ McNamara's test at alpha 0.01. Results. So we saw some really good performance. The key results, the first one is that we saw 47-second mean threat anticipation lead time. We're talking of threat anticipation with sigma of 4.3 seconds, confirmed statistically significant versus ZTA baseline with McNamara chi-square at 24.6. That is significant. We saw 83% false positive reduction from 12.4 to 2.1 due to the JEPA engine's contextual understanding of normal infrastructure trajectories. We also saw 87% MTTIC improvement from 340 down to 45 seconds, validating H2, which required at least 70% improvement, and 72% residual operational capacity at 60 minutes under coordinated cascading attacks. All 3 hypotheses are confirmed with strong statistical significance. The left figure shows a ROC curve, or a number of ROC curves. The first one is our SZTIGA achieves AUC of 0.987, substantially outperforming standard ZTA at 0.871 and traditional IDS at 0.808. The right figure shows trust score temporal evolution during an attack scenario. The key insight is the 47-second prediction lead time. The JEPA engine detects the emerging threat in the latest space well before the attack materializes, enabling preemptive trust score degradation and identity containment. Oblation was a key part of what we really wanted to do. The oblation study removes 1 pillar at a time. Removing JEPA causes the largest drop in anticipation from 47 to 11 seconds at 76% reduction. Removing the identity access causes the largest degradation in containment. MTTIC increases from 45 to 180 seconds at 300% increase, because without identity-centric enforcement, the system essentially falls back to network-based isolation. Removing governance, on the other hand, what we saw is that when we took out governance, primarily impacts resilience under cascading scenarios, 72% down to 51%. The radar chart on the right side visualizes all 3 pillars contribute independently across the performance dimensions. All ablation comparisons are statistically significant at p less than 0.00 1. Performance analysis reveals meaningful variance across domains and attack types. Across domains, defense networks achieve the highest accuracy at 99.1, with the lowest false positive rate at 1.2% due to stricter identity controls and fewer identity principals. In vehicle to anything environments, this show lower performance with 96.9 accuracy and 2.1 FPR due to high mobility and high churn identity environments. Across attack types, identity spoofing detection is the strongest at 99.2%, where behavior deviations are most pronounced. AI-enabled adaptive attacks are also hardest at 94.3% detection and 5.7% false negative. As adversaries evolve in response to defenses, we saw that this informs deployment-specific tuning recommendations, and you're going to see that in our recommendations. On the left side, FPCR convergence curves under 3 conditions. What we saw is that there were degraded conditions, which is slower but still achieves 0.98 within 90 seconds. The OPL push-based mechanisms outperforms pull-based, as we can see. And finally, the predictive containment prevents cascade propagation by hardening identity controls at anticipated domains. The key implications worth mentioning here is that identity is better than network in terms of identity as a sovereign control plane. We saw that AI agent governance should be a first-class citizen, and we also want to see some kind of interoperability as the confidence, calibration, and attention attribution plus operator override becomes crucial. Some limitations that we observed was that we use simulation. We would like to do this in a real production environment. Scalability-wise, we need to test this in more objects, and then we also face some regulatory constraints. Finally, in the future, we hope to do some real-world pilot. We also hope to test this in a post-quantum environment. We would like to have some formal verification, and then we would also like to do this on federated learning. I want to mention that these some key contributions, just as a summary. Federated identity management as sovereign control plane for national critical infrastructure is crucial. JEPA-based predictive threat anticipation performs better. AI agent identity lifecycle governance should be the norm. Formal trust scoring via GP with Thomson sampling was achieved. We brought in some novelty in terms of MTTIC, PTH, which is pass the hash, FPCR, with statistical validation. In conclusion, I would like to thank everyone for listening in, and I welcome your questions either via email or any other means of communication.